At the 1980 annual ASA meeting in Houston, Dr. Deming made an appearance before us, not in person, but in an NBC film documentary entitled "If Japan Can, Why Can't We?" This film, shown at that meeting, highlighted Dr. Deming's impact on Japan's industrial quality. We are very pleased to have him with us today in person. Dr. Deming's formal education culminated in a PhD degree in mathematics and physics awarded from Yale, and his early career was devoted principally to studies of physical properties of matter while serving in several U.S. government organizations. During this time, he generated a strong interest in theories of errors of measurement and statistical sampling and made innovative contributions to these areas. He has been for 30 years a consultant in statistical studies with practice worldwide. A partial listing of his clients include railways, telephone companies, carriers of motor freight, automotive companies, and hospitals. He is perhaps best known for his work in Japan, which commenced in 1950 and sparked a revolution in quality and economic production. The Union of Japanese Scientists and Engineers instituted the annual Deming Prize to be awarded to a Japanese scholar for contributions in statistical theory or its application, and a medal to a Japanese company for use of statistical methods for advancement of precision and dependability of its products. In May 1960, he was decorated by the Emperor of Japan with the Second Order Medal of the Sacred Treasure. He has received the Schuart Medal from the American Society for Quality Control. He is the author of several books on statistical methods and over 150 papers. Since 1946, Dr. Deming has been a professor of statistics at the Graduate School of Business Administration of New York University and has lectured in numerous universities in this country and abroad. The title of his presentation is "The Teaching of Statistics in the Industrial Crises that Confronts the Western World." Dr. Deming.
It is a pleasure to be here amongst friends. In fact, so many friends. I must remind you that all statisticians are friends. My observation is that any statistician will help another and will look for ways to help him to improve his practice. My criticisms of statisticians and of the teaching of statistics this afternoon, you will believe me, I'm sure, are only my attempt to help statisticians to render better service to industry and science. The statistician's job in industry or in any other place is not just to give first aid treatment to problems brought to his attention, but to find problems that no one else can find, and to lay out procedures for solution. For example, the 14 points for management to work on for the restoration of American industry, as I see it, came from observations in statistical practice. These 14 points are an outline as follows. Number one, innovate. Prepare for the long pull. Allocate resources to fulfill the long-range needs of the company and of the customer. Short-term profits are not indication of good management. Anybody can pay dividends by deferring maintenance, cutting out research, or by acquiring another company. Paper profits are not indication of either intelligence, knowledge, or skill. Innovation requires resources, faith in the future, putting resources into plans for product and service for the future, putting resources into education, preparing for the long pull, putting resources into maintenance of equipment, furniture and fixtures, new aids to production in the office and in the plant where they would be effective, to learn about the deficiencies of the product or service being offered today. Intensify attention to the needs of the consumer. Learn how the consumer uses the product, how he misuses it, and how to improve tests of the product and service. It is a mistake to suppose that statistical quality technology applied to products and service offered at present can with certainty keep an organization solvent and ahead of competition. It is possible and in fact fairly easy for an organization to go broke, making the wrong product or offering the wrong type of service. Even though everyone in the organization performs with devotion, employing statistical methods and every other aid that can boost efficiency. Number two, learn the new philosophy. We are in a new economic age. We can no longer live with commonly accepted levels of mistakes, defects, materials not suited to the job, people on the job that do not know what the job is and are afraid to ask, handling damage, failure of management to understand the problems of the product in use, antiquated methods of training on the job, inadequate and ineffective supervision. Acceptance of defective materials and poor workmanship as a way of life is one of the most effective roadblocks to better quality and productivity in America. The Japanese faced it in 1950. Unreliable and non-uniform were kind words for the usual quality of incoming materials in Japan in 1950. Good workmanship was impossible. Japanese management took aim at the problem and in time reduced it to a level never before achieved. American industry today faces the same problem. The road that Japanese manufacturers paved would be a good one for American management to copy. The only trouble is you cannot copy. They did not copy America. American industry cannot copy Japanese. Number three, make it clear to vendors of critical parts that they must learn and use process control by statistical methods. There is no other way for them, nor for a company, to know the quality that is coming in, and no other way to achieve best economy and productivity. Purchasing management must learn the statistical control of quality. How many? Hundreds in many companies, thousands, tens of thousands in the country. Look at the job ahead. Who's going to teach them? They must proceed under the new philosophy. The right quality characteristics must be built in without dependence on inspection. Statistical control of the process provide the only way for the supplier to build quality in, and the only way to provide to the purchaser evidence of uniform, repeatable quality and cost of production. Number 4. For most companies, this will mean a drastic reduction in the number of vendors that they deal with. In particular, they must abandon the practice of having 2, 3, 5, 11 vendors for the same product. A multitude of suppliers enlarges severely the problems of ascertainment of evidence of quality. The theory that competition automatically regulates quality and price does not work in today's requirements for uniformity and reliability. Price has no meaning without a measure of the quality being purchased. Without adequate measure of quality, business drifts to the lowest bidder. The quality and high cost, low quality and high cost being the inevitable result. American industry and the U.S. government are being rooked by rules that award business to the lowest bidder. That competition does not regulate quality and price may sometime reach regulatory agencies. The purchasing managers of a company are not at fault for giving business to the lowest bidder, nor for seeking more bids in the hope of getting a still better price. This is their mandate from the top management. Only the top management can change their direction. The 14 points that I am describing, you see, must be undertaken by top management. Only they can bring these things about. They need help, and everybody in the company must help. But without top management, American industry cannot improve. Number 5, use statistical methods to find out in any trouble spot what are the sources of trouble, which are local faults, which faults belong to the system, put responsibility where it belongs. You can do that only by statistical methods, not on judgment. No amount of knowledge of engineering, nor psychology, nor chemistry, nor physics, or production processes can give the right answer. Statistical methods must be used. Most of the problems belong to the system and are the responsibility of management. Dr. Duran put the percentage at about 85 for the system and the responsibility of management, and the other 15% to the workers on the job. A totally different picture from what is commonly supposed. Management must constantly improve the system. Number 6, management must institute statistical aids to training on the job. Training must be totally reconstructed. Books on training, practices on training will have to be changed drastically. Statistical methods, only statistical methods will tell you when a man is trained and when he is not yet trained. And when he is trained, you cannot train him further by the same methods. You hired him, you trained him. He turns out defective. What are you going to do? You have only one chance. Do it right. The only thing that you can do is find another job for him and try to train him better on the other job. Number 7, improve supervision. No one could possibly understand the magnitude of this job nor the importance of it without a long treatise, a long session on the subject. The problems are terrific. Foremen must have more time to help people on the job. Statistical methods are vital as aid to the foreman and to the production manager to indicate where fault lies. Is it local or is it in the system? Only a control chart or similar statistical method will tell you the answer. Judgment is not the answer. Judgment is hazardous. The usual procedure by which the foreman calls a worker's attention to a defect may be wrong, is certainly wrong in most organizations, and defeats the purpose of supervision. This is just one little item of many that must be changed. Number 8, drive out fear. Most workers, and even people in management, do not understand what the job is, nor what is right and what is wrong. Moreover, it is not clear to them how to find out. Many of them are afraid to ask questions or to report trouble. Trouble with equipment, trouble with materials that they're trying to use. The economic loss from fear is appalling. It is necessary for better quality and productivity that people feel secure. SE, from the Latin, means without. Cure means concern, fear. Secure means without fear, not afraid to ask, not afraid to comment, not afraid to offer a suggestion, not afraid to do the job. A dialogue recorded for me by a friend read like this on the job. A millwright on the job. To the foreman, this bearing is getting warm. We ought to do something about it and do it now before it freezes and carries the shaft along with it, perhaps. And the foreman says, we can't stop now, not now. We have to get our quota out, our quota of castings. We have to get them out. The bearing freezes on the foreman's shift, takes the shaft along with it, and the whole production line is shut down for 4 days while they get a new shaft from Baltimore. Typical. Why? Because the foreman cannot work for the company. He has to work for the foreman. That's his mandate, to get this stuff out, no matter what. Fear. A terrific toll. 9, break down barriers between departments. People in research, design, and sales must learn methods of production and learn about problems encountered with various materials and specifications. Otherwise, there will be losses in production from necessity for rework and from attempts to use materials unsuited to the purpose. Why don't these people spend time in the factory? Follow me around. See the problems in advance, not after it's too late. Any statistician sees the problems any day. Number 10, eliminate numerical goals for the workforce. Slogans, posters, pictures, urging people to increase productivity. Sign their work as an autograph. 0 defects. These devices are management's lazy way out. They indicate desperation and incompetence, despair, hoping that somebody will pull them out. Number 11, look carefully at work standards. Do they take account of quality or only of numbers? Do they help anybody to do a better job? Work standards are costing the country as much loss as poor materials and mistakes. There's a better way with the help of statistical methods. Number 12, institute a massive training program for employees in simple but powerful statistical methods. Your purchasing departments, the whole force of management, supervisors, people that train, everybody on the job must learn statistical methods. Some must learn more than others. Thousands of people must learn. In one company that I work with, they're going to train 50,000 people. Not next week. It's going to take a long time. But they're going to do it. Number 13, institute a vigorous program for retraining people in new skills to keep up with changes in model, style, methods, materials, and at times, if advantageous, new machinery. There's too much talk, incidentally, about need for new machinery and automation. Most of it's nonsense. Most people have not to learn to use what they have. With more time, I could give many illustrations. Remember this. In Japan, where they are using present equipment to the best advantage and no further capacity can be squeezed out, there is only one way out to increase production, and that is by automatic machinery. There is no labor force to draw from. There are no unemployed to draw from. Everybody is at work. I'm not an economist, but I see quite different conditions here. I read about figures on unemployment. Those different economic conditions required different points of view. One cannot copy unless he knows what he's doing. Number 14, make maximum use of statistical knowledge and talent in your company. Provide statistical guidance, statistical teaching. Well, those are the 14 points. Anybody can see that this is a long pull. How many years? 10 years may show a difference, 15, 20, 30. Neither American management nor the teaching of statistics will be recognizable by that time. American industry can move along only with the help of statistical methods. But statisticians are not helping. My ultimate aim is improvement of statistical practice. Improvement will come from better teaching and better textbooks. Also from guidance to people that are doing statistical work in industry. It'll be a long pull, as I have said. A number of simple but essential statistical principles capture the imagination of young people. Operational definitions are an example. In my experience, high school students are fascinated with the logical exposition of the fact that an object cannot be exactly round, that arrival at exactly 3 o'clock cannot be defined, that there is no true value for the speed of light, nor for the number of defective items in a lot, nor for the number of inhabitants of Detroit. They are equally fascinated, these young people, in my experience, with the fact that the label on a blanket reading 50% wool can have any one of 100 meanings, none right and none wrong, for the simple reason that the choice of definition depends on the purpose of the test. It is a further interest to them that there is one possible set of meanings for purchase of a single blanket and a whole new set of meanings for purchase of a run of blankets, as for an army, for a hospital, a large retail store, or a wholesaler. Some high school students of today, if introduced expertly to the study of statistics, and some of the points that I've just mentioned, for example, would pursue statistical studies in later years and make contributions to research and industry. And you may say, well, that's a long way off. It is a long way off. American industry faces an equally long period of time to reach competitive levels. Challenges face statisticians today as never before. The whole world is talking about safety in mechanical and electrical devices. In automobiles, for example, safety in drugs, reliability, due care, pollution, poverty, nutrition, improvement of medical practice, improvement of agricultural practice, improvement of quality of product, breakdown of service, breakdown of equipment, tardy buses, trains, and mail, need for greater output in industry and in agriculture, enrichment of jobs. The consumer requires month by month ever greater and greater safety, and he expects better and better performance of manufactured articles and of service. The manufacturer has the same problems in his purchases of materials, assemblies, machines, and use of manpower. He must, in addition, know more and more about his own product. These problems cannot be understood. They cannot even be stated. Nor can the effect of any alleged solution be evaluated without the aid of statistical theory and methods. One cannot even define operationally adjectives like reliability, safe, polluted, unemployed, on-time arrivals, equal in size, round, random, tired, red, green, or any other adjective for use in business or in government except in statistical terms. Likewise, a standard as of safety, or a performance or capability, or a government regulation. What is due care? What is care in manufacture? Care can be defined in operational terms with the aid of statistical methods. Due care cannot be defined. It has no communicable meaning. It requires no imagination to perceive this distinction between care and due care is important for lawyers as well as for engineers. We are in a new economic age brought about by an intelligent management of statistical techniques in Japan. Economic laws of competition, long worshipped by scholars and by industry and by government, must be rewritten. By industry, I include service organizations, such as career functions in federal, state, and local governments, police and fire departments, along with hospitals, medical service, legal service, banks, transportation of freight, transportation of people, entertainment, wholesale and retail sales, service on automobiles and on other equipment, architects, construction, telephone and telegraph service, and other services of communication, including the mail. Anyone that has ever registered at a hotel can appreciate the woeful waste of human effort on both sides of the counter for what could be a simple operation. Use of electronic machinery instead of hastening the procedure has, in my observation, drawn it out. The Disappearing Act, he did it 3 times last night. And the girl alongside of him, serving a friend of mine, did the Disappearing Act also 3 times. It requires training to do that. Those are not accidents. The problem that American management faces is that there are only a pitifully few statisticians that are willing and able to tackle the problems of industry. In my experience, people with fresh doctorates in statistics are helpless in industry. Let me go a little further. I'd say that they're a hazard. They do not learn. They do not improve unless they have the good fortune to work under the guidance of a competent, experienced statistical consultant. Practice is more exacting than pure science. Schuhart said it, it's still true. The standards of knowledge and workmanship required in industry and in public service are more severe than the requirements of pure science. He could have added that the requirements for statistical practice are also far more rigid than the requirements imposed on the teaching of statistics. The only empirical use of any knowledge is aid in prediction, analysis of variance, t-tests, chi-square, and kindred tests are nearly always, in practice, wasteful of data and solve the wrong problem, if any problem at all. No statistical test can evaluate the probability of a specified outcome in the future. Unfortunately, the limitations of statistical tests are not taught in the textbooks, and students have little chance to learn about the needs of industry and to learn techniques that might be helpful. It is necessary, when we investigate the improvement of statistical practice, to think of two types of problem. I call them enumerative and analytic. You may, if you wish, change the word enumerative to descriptive, as suggested by my friend Dr. Kolar of the University of Mainz. You may change the word analytic to comparative, if you wish, also at Dr. Kolar's suggestion. Words do not solve the problem, but they help. In the enumerative problem, or descriptive, the aim is better knowledge about a frame, about the material in a frame. In the analytic problem, there will be action. The aim is to obtain information by which to take action on a cause system that produced material or service in the past and will produce material or service in the future. One meets both problems in practice. The methods of statistical design and of statistical inference are different in the two types of study. Failure to make the distinction between them has led to uninspired teaching of statistical methods and to woeful waste of data in practice, and to impairment of service that statisticians could render. An example of an enumerative study is the census. Another example could be a quick count of the number of people left without homes and without food by a flood or earthquake. A vital question is how many people, how many adults, how many infants, how many infirm are in need of the necessaries of life. Another example is the census of a city taken as a basis for increase in financial support from the state. Cores board from bales of wool as they are unloaded from the ship in Boston. 6 million pounds of wool. Determine the value of the wool in dollars and the duty to be charged by the Bureau of Customs. Accounts receivable, another one. Estimate from a sample, from an inventory of material, the proportion thereof that is defective or impaired by age. Estimate by a sample of boring the number of kilograms of iron pellets that disappeared from a storage pile into the ground below. Estimates from a sample in the enumerative study are estimates of what the equal complete coverage of the same frame would give. The equal complete coverage would be carried out by the same definition, same procedures of investigation, same investigators, same care. It would be subject to the same proportion of care and of carelessness, wrong answers, and the same proportion of non-response as characterized the work on the sample. A sample less than 100% will lead to estimates that differ more or less from the equal complete coverage. Repetition of the sampling procedure is possible in an enumerative study. In fact, comparison of the results of interpenetrating samples provides a basis for instant estimation of the standard error of the result of the aggregation of the samples. Mahalanobis, 1933. Moreover, the standard error in an enumerative problem has operational meaning, except in case of high skewness and samples not large. Confidence limits, accordingly, have operational meaning in the enumerative study. They are predictions. Further samples can be drawn and equal complete coverage as possible, in principle at least. Comparisons can be made. The meaning can be translated into prediction. In contrast, as we shall see, calculation of a standard error in an analytic problem, comparing treatments, for example, is merely an exercise in arithmetic. We can make two kinds of mistake in an enumerative problem. We can, number one, pay too much for the shipload of iron ore, for example, or we can pay too little, one being the buyer's risk, the other is the seller's risk. A loss function can be written down and it can be evaluated by some preliminary samples. And the expected net loss from additional samples, including the cost of sampling and testing, can be minimized by appropriate design. No such calculation is possible in an analytic study. Why? Because we are not sampling from a constant cause system. The cause system is on the fly, and we know not where it will be for the next experiment. For patients to be treated, the aim in an analytic study is to provide guidance in the intervention of a cause system. The cause system produced the material studied. Industrial product, crop of wheat, service, customers, patients, share of market, economic conditions. The cause system will be different in the future, whether by intervention or through natural changes. One exception is a process that has been brought into a state of statistical control, in which case the state of the product or operation or service has a stable distribution hour after hour, day after day. Statistical theory then applies to the material or process produced. Examples occur in nature. For example, radioactive disintegration. The aim of intervention is to achieve greater uniformity of product in the future and more of it, or greater outturn of wheat, more frequent service with fewer mistakes, more patients that show improvement, more customers, better economic conditions. Intervention may be merely to leave the process alone or to hold on to the standard treatment. But another way, the aim in an analytic study is to try to learn something about the cause system, to be in position to change it or to leave it alone. The material studied in an analytic problem is not of interest in itself. You see, in total contradiction, total contrast with the frame in an enumerative study. A complete census, such as a study of all the people in an area, or all of last week's product, is still only a sample of what the cause system can produce, and in fact did. The design in an enumerative study is totally different from the design in an analytic study. What people are learning in textbooks and in classes is the theory for enumerative studies, not for analytic studies. One may make either one of two mistakes in an analytic study, simplest thing in the world to make either mistake. We may adopt treatment B in preference to A, only to regret it later. Or, two, we may fail to adopt B, retain A, only to regret later our failure to adopt B. One may make either mistake, with or without the help of statistical data, and with or without higher education. The aim of statistical methods should be to strike the net economic loss between the two mistakes. Unfortunately, as I see it, that problem has not been treated by statistical methods except by the Shewhart control charts. My listeners may justly expect me to come up with improvements of statistical theory for analytic problems, and not merely to criticize what is being taught and written today. This I must do daily in my own practice, and any statistician does in practice. I'm not prepared, however, at this time to write a new textbook. A few crude examples, however, may illustrate what needs to be done. We may pause first to elaborate a bit. Let us turn back to R.A. Fisher's great contributions to the theory of estimation. Please note that these contributions apply only to enumerative problems. He presumed the existence of a stable distribution and the possibility to draw sample after sample from this distribution. Unfortunately, a stable distribution is untenable in an analytic problem, except, as I have mentioned, in the state of statistical control. Fisher's words are very clear. Any body of numerical observations or qualitative data thrown into numerical form as frequencies may be interpreted as a random sample from some infinite hypothetical population of possible values. What Sir Ronald thus described is an enumerative problem, the ability to repeat over and over the sampling procedure from a stable distribution. No such condition exists in an analytic problem. It is misleading, it seems to me, to invent and imagine the existence of a hypothetical infinite stable set of random numbers that we can draw from when no such thing exists, when we know that it does not exist, merely to be able to use certain statistical theory that one has learned and loves. The standard error in an analytic study has no predictive value, as the environmental conditions of the experiment will not be repeated. We will not apply the results to the patients that we have tested, nor to the land that we've used for our experiment. Statisticians would do better, I believe, to provide statistical methods that are helpful to the problem at hand. And as I have said, any statistician in practice does that every day. The teaching of statistics today, as I see it, resembles an attempt to teach a child to talk by first teaching the poor little fellow syntax, word order, comparative word orders in English, French, and Japanese. He would become the school psychologist's chief problem, and he would never learn to talk. Fortunately, as the world goes, he learns to talk by imitation and by the need of communication. In the manufacture of a certain brand of wire, the desired diameter is 0.06 centimeters. If the mean thickness of the individual wires is above or below this value, then the machinery must be adjusted. Anybody that did that would be fired summarily, or ought to be. Because the amount of production time lost during adjustment is considerable, historically it has been established that the standard deviation is about 0.003 centimeters. Each day a random sample of 100 wires is selected, and based upon the samples, a decision of whether to adjust the machine is made. A. State the two hypotheses H sub 0 and H sub 1 in algebraic form. Is the test lower-tailed, upper-tailed, or two-sided? And so on. You can imagine the rest. Pick up any book and you will find it. Does adjusting the machine correspond to accepting or rejecting H0? Calculate the critical values for the test statistics and then formulate the decision rule. Calculate the type 2 error. Can't be done. Sir Ronald probably knew what he was doing when he paid no attention to the type 2 error. He may have been smart. What is wrong with this exercise? Everything. The actual problem is in practice when to adjust the machine and when to leave it alone, and whether changes in the system, the responsibility of management, would be desirable. It would be so much better, infinitely better, to take 25 samples of 4 successive wires at intervals during the day. I mean, if you insist on taking a sample of 100, let's do it so that we get some information, not just figures. Take 25 samples of successive 4s during the day. Draw up an X bar and R chart. If the process is in control and the thickness of the wire is right, leave it alone. And if the points stay in control, leave the process alone, except for changes in the system that only the management can make. Actually, a much smaller workload would suffice than 25 samples of 4. You don't need anywhere near that many after the first few runs. A sample of 4 successive wires every half hour at first. Then when special causes are weeded out, or what Dr. Schuhart called assignable causes, maybe a sample every hour or a sample every 2 hours would suffice. As a remark, the standard deviation that I mentioned in the statement of the problem, standard deviation of the diameters of the wires, does not exist except as a mere exercise in arithmetic, unless the process is in statistical control. Example number 2. A proposal for teaching statistics to hundreds of people in a company, the aim being to improve quality and productivity. 15 weeks. Drawn up by a man just received a doctor's degree, gone to work in industry. The outline reads as follows. I will not read it all. Ungrouped frequency distributions. Number 2, grouped frequency distributions. 3, functions of a frequency distribution. Confidence limits. Review of descriptive measures. Probability. Probability distributions and expected values. Emphasis on continuous random variables and the normal distribution, which one never has. Sampling. Need for sampling. Bias and error in sampling. Selecting the sample. All that's good. Distribution of X bar and the normal distribution. Statistical estimation. Testing hypotheses. Chi-square and analysis of variance. Some non-parametric statistics. Good. Regression and correlation analysis. Good. What's wrong? Starting the child off with syntax, comparative word order, when the poor fellow needs to learn to talk. He needs to communicate. He wants to know what the problem is. This is the wrong way to start. This comes a long time after the start. In the first place, you see, a distribution does not exist until you have made a distribution. Oh yes, you can take 100 numbers and calculate a mean and the standard deviation. Anybody can do that. But it doesn't have any application unless you have stability, that is randomness, and that is statistical control. And statistical control has to be achieved. It is not a natural process in a company. So all this work about distributions is at the wrong end. First of all, the job is to get a distribution. And in getting a distribution, that is, in achieving statistical control, what the statistician contributes is 10%, 20%, 30%, 40% to the productivity and hence to the capacity of the process. I think many statisticians are not aware of the fact, merely a matter of words, that as you improve the quality of a process, you naturally improve its productivity. Yes, of course. But another way to put it is, as you improve the quality of a process, you improve the capacity of the process, your ability to produce more. Instead of new machinery, maybe what you need is learn to use what you have. You should see some of the letters I get about all this fancy new machinery. It didn't work. You see, technically, the fault in this outline that I just read is that it teaches enumerative methods. All the main problems in the industry are analytic. For example, the topic, test for equality of several proportions, has no place in industry. We know in advance that proportions from several sources will be different. Why try to find out what anybody knows? Why spend money to find out what anybody knows? Why not ask the right question? Then you have some possibility to get the right answer. Whether their proportions are significantly different is a question far removed from the needs of industry. That has nothing to do with the case. The proportions will be different if the sources are different. That's not the problem. The problem is, how different are they? And should we choose one of the sources over the other one? And you cannot do that by analysis of variance. We can be thankful that schools of medicine do not turn out students taught totally, wholly by theoreticians, chemists, pathologists, and the like, with no learning from men in practice and without some attempt to learn from them. Interchange between industry and universities for the teaching of statistics might be an idea worth exploring. Thank you.